So let's take an example. So let's take one-dimensional heat conduction equation. So this is one dimensional. Let's suppose I have a rod which is being heated. This is my domain, and the governing one-dimensional heat conduction governing equation is governed by the Fourier law. One-dimensional Fourier law is given as d by dx. K is the thermal conductivity of material, dt by dx, the temperature, the dependent variable, plus some source term is equal to 0. Very simple one-dimensional heat conduction equation. Now we want to apply this governing equation over this one-dimensional domain. Now what we are going to do is we are going to divide this domain first through some control volumes. So let's choose some control volumes. Let's suppose this is my first control volume, this is my second control volume, this is my third control volume, this is my fourth control volume, and this is my fifth control volume. So each control volume will be incorporating a grid point at its center. Okay, so how many grid points? 1 2 1 2 3 4 5, but we will also include the boundary grid points as well for the boundary conditions. So we'll have 1 2 3 4 5 6 7 grid points. So in finite element method, how we have discretized the similar thing. So what we have taken the nodes as my grid points, and we don't care about what's happening at these intermediates. We just care about what's happening here, right, in finite element methods. But here we are interested what's happening as a whole inside this control volume, right? So what we'll do is we'll take one control volume. Let's suppose fourth control volume. So my fourth control volume will look something like this, and we'll call this control volume with generic name P, capital P, let's suppose. So this is my P, okay, and the 3 and 4 nodes are 3 and 5 nodes are written in this manner. So this is my P, this is my west element, this is my east element, right? And this is my west face with small, this is my east face with small letters. So the control volumes grid points are denoted by these bigger subscripts, and the faces are denoted by the small subscripts. Okay, so this is my west face, this is my east face, this is my east element or the east control volume, and this is my west control volume, and this is my the control volume we are interested in. Now next task is to here this is, since this is a one-dimensional problem, so we need not to convert we don't have to need not to convert volume integral to surface integral. Why? So just this is just a one-day element, so just integrating through dx will work, right? So we can write it as this as d by dx. So volume integral should be converted into surface integral will be needed in the three-dimensional problems or two-dimensional problems, not in one-dimensional problems. So we can, it's an easy approach towards the problem for one-dimensional equation. So now we are going to apply the finite volume method for the one-dimensional condition. D by dx k dt by dx plus s is integrated over dx domain is equal to 0, and we will integrate it via from west to east, right? From here to here, from west to east face on one particular control volume I'm applying. Now what we can do, we can write w e small e d by dx k dt by dx plus west to east s dx is equal to 0. Now what we can do, we can integrate it and we can write k dt by dx from west to east plus s, and we should also write the length of these elements. So from east to west, this control volume will have a length of delta x, and from P to E, capital P to E, the length is del xe, and from P to W the length is del xw. So this length here from E to W is nothing but delta x is equal to 0. Okay, now we are closer towards discretizing it, but the problem is we still need to deduce the value of dt by dx at E and W. So what we are going to do is we are going to assumption of profile assumption, right? What profile we need to choose here? I think slope at the faces, right? The slope at the faces. So let's look more clearly here. So let's take this example in next page. So this was my P element, P control volume. This was my E control volume. This was my W control volume, and this was my east face, and this was my west face, and this constitute a control volume, right? So what we need to do here, we need to do the profile assumption dt by dx, I mean slope of this function at uh, east and west faces, so here and here. So what are the options we have? What are the options we have? We can choose a continuous function like this, so we assume that my temperature at P is continuous here, piecewise continuous rather. We will assume that our profile assumption is piecewise continuous, and that is sufficient to approximate. So what is the advantage of taking the linear? So basically this particular assumption is linear, piecewise linear over the faces. So at this E face, what we are getting, the slope is linear, slope is continuous. What if we could have taken the higher order, I mean polynomial assumption or quadratic functions? We could also do that, but there is a disadvantage to that, since let's suppose I am assuming piecewise continuous function like this. Okay, but here my piecewise continuous function is something like this, in this domain, in W to P. So here what we are seeing, that E is having two different slopes, so which is not a acceptable solution. So we are going to ignore higher order approximations, and linear piecewise continuous function is sufficient to approximate the solution. So piecewise linear means we can now approximate my dt by dx at this point from E to W. So what we are going to do is dt by dx at E to W, I can write dt by dx at E minus dt by dx at W. We are going to substitute it in this equation. Let's write this equation again. So this is my let's write that equation again. K dt by dx west to east plus s dx is equal to 0. So we can substitute this equation here, and we can write k dt by dx at east face minus k dt by dx at west face plus s dx is equal to 0. Okay, and also this these slopes at E and W faces can be written as TE minus TP divided by del XE. So this is my, from P to E I have assumed that this length is delta XE and this length is delta XW. So this minus TP minus TW divided by delta XW. So I can safely write this as this. So in the next, okay, so here also here itself I will write k times te minus tp divided by delta xe minus k tp minus tw divided by delta x w plus s delta x is equal to 0. We can write this equation in uh, uh, another another page as also. So far we have considered that these k's are constant, but for the sake of more generality, we can write this k at E face is ke and this k as kw. Let's suppose my thermal conductivity is also changing with the domain length, so I can write ke te minus tp divided by delta xe minus kw tp minus tw capital W. Okay, all these are capital, sorry. Tp minus tw divided by delta xw plus s delta x is equal to 0. I can club the Tp terms in this fashion. So let's suppose this is my Tp times, I will write ke by delta xe, ke by delta xe plus kw by delta xw, right, times Tp is equal to, we get things in one side and we can write ke divided by delta xe times te plus kw divided by delta w times tw minus s delta x is equal to 0. I'm sorry, this is my, so Tp minus this term is equal to 0. All these terms we can write like this. Let's also assume that this particular term we call it AP, this particular term we call it AE at east, this particular term is west, and this is my B term. Now we can write as a whole as APTP is equal to, let all these terms move into right hand side, AETE plus AWTW plus B. Essentially this is the discretized algebraic equation for one particular control volume. So essentially if P is your ith node, capital E is your I plus 1th node, capital W is your ith minus 1th node. So essentially this is for ith term, this is your I plus 1th term, this is your I minus 1th term. So see, your ith node is influenced by I plus 1 and I minus 1 nodes, and you can write for all control volumes, and you can club this is in the form of Ax is equal to B types equation. You can invert it and you can get the solution of all TPs in one go, right? So that's it for today's lecture. Tomorrow what I will do is I will go for the more examples maybe I'll start with two-dimensional finite volume method. I'll take a more realistic problem. We can also go for several schemes such as quick scheme, upwind scheme, etc. uh, okay, so that's it from the today's lecture. Thank you.